in the previous lecture we were discussing the solution of the Legendre's equation. So, we will continue our discussion on the angular momentum problem. So, in my last lecture we had considered the solution of the differential equation d2f by dx square minus 2x df by dx plus lambda f of x, where lambda is the eigenvalue. We solved this by a power series method, and we showed that the solution of the above differential equation can be written as, it can be split into two series, a0 plus a2 x square plus a4 x4 plus a1 x plus a3 x cubed plus a5 x5 and so on, and that ar plus 2 divided by ar was equal to r into r plus 1 minus lambda divided by r plus 2 into r plus 1. This is the recurrence relation that we had discussed last time. Now, since this tends to 1 as r tends to infinity, so if the series remains an infinite series, it will diverge at x equal to plus minus 1. We cannot let that happen, because the wave function has to be always finite, and so therefore, we must terminate the series or make it into a polynomial. Either of these series will become a polynomial only when lambda is equal to L into L plus 1, L into L plus 1, where L can be 0, 1, 2, 3, etc. And we will show just now that when L is 0, 2, 4, etc., the even series will become a polynomial, and the odd series will be an infinite series. So, there are always, for a second order differential equation, there are always two solutions, and we will show that for these values of L, one of the solution is a polynomial. In general, both solutions are divergent at x is equal to plus minus 1. Only for certain specific values of lambda will one of the solution be well behaved and will be a polynomial, and the other series will again be ill behaved at x is equal to plus minus 1. And when L is 1, 3, 5, etc., then this series will become a polynomial, the odd series will become a polynomial, the even series will remain an infinite series, and therefore, a0 we must put equal to 0. So, in my last lecture I had assumed L is equal to 2, so lambda was 6, and if lambda was 6, then ar plus 2 divided by ar will be r into r plus 1 minus 6 divided by r plus 2 multiplied by r plus 1, and we had obtained that a2 by a0, that is r is 0. So, this is equal to minus 6 by 2, that is equal to minus 3, and a4 by a2. So, r is 2, 2 into 3 is 6. So, this is equal to 0. So, my polynomial solution becomes, which is given by L is 2. So, we write it as P2 of x, because this implies lambda equal to 6 implies L is equal to 2. So, P2 of x, this is equal to a0 1 plus a2 by a0. So, 1 minus 3x square. We now choose the coefficient a0 such that such that the P2 of 1 is 1, and so therefore, we write P2 of x will become half 3x square minus 1. That is, to satisfy this condition, we must choose A0 is equal to minus half. So, this is the polynomial solution, and we must choose A1 equal to 0, so that the odd series is not there. So, therefore, for lambda is equal to 6, this P2 of x is the well behaved solution of this. Now, let me consider another example. Say we take L is equal to 3, So, then lambda will become 12. Sorry, before that I must show that if I take lambda is equal to 6, I again use the recurrence relation AR plus 2 divided by AR is equal to R into R plus 1 minus 6 divided by R plus 2 into R plus 1, and we will show that the odd series remains an infinite series. Let us see this way, just look at the numerator. So, A3 by A1, so R is 1, so 1 into 1 plus 1 is 2, 2 minus 6, that is 2 minus 6, and this becomes 3 into 2, that is 6. So, this is minus 4 by 6. A5 by A3, this becomes R is 3, so 3 into 4 is 12 minus 6, that is 12 minus 6 is plus 6 divided by R is 3, 3 plus 2 is 5, 5 into 4. Whatever it is, you see it has changed sign, minus to plus. Then if I calculate A7 by A5, that will be also positive. So, R is 5, so 30 minus 6 will be 24 divided by something. So, none of the coefficients will become 0. So, therefore, when lambda is 6, the odd series will be an infinite series, and hence we must choose A1 equal to 0. So, therefore, this is the well behaved solution corresponding to lambda equal to 6. Let me take another example, and let me assume L is equal to 3, then lambda is equal to L into L plus 1, so that is equal to 12. Once again, let me do this, AR plus 2 divided by AR, this becomes R into R plus 1 minus 12 divided by R plus 2 into R plus 1. Now, let me take the even series first. So, let me write down A2 by A0. So, R is 0. So, this is minus 12 multiplied by 2. So, this is minus 6. A4 by A2. So, R is 2. 2 into 3 is 6, that is minus 6 divided by 2 plus 2 is 4 into 3, whatever that number is, it is a negative number, and then A6 by A4, R is 4. So, this becomes 4 into 5, that is 20 minus 12, that is plus 8, and so therefore, this is 6 into 5. So, this has changed sign, and therefore, for lambda equal to 12, the even series will remain an infinite series, and therefore, we must choose A0 equal to 0. Now, let me consider the odd series. Let me write down A3 by A1. So, R is 1. So, this becomes 1 into 2, that is 1 into 2, that is 2 minus 12 is minus 10. 1 plus 2 is 3, 1 plus 1 is 2. So, 3 into 2 is 6. So, this becomes minus 5 by 3. And then A5 by A3. So, R is 3. So, this becomes 3 into 4, 12 minus 12. So, that is 0. And so, therefore, A7 equal to A9, they all will be equal to 0. So, you will have, if the polynomial solution will be f of x is equal to A1 x plus A3 by A1, that is minus 5 by 3 x cubed. I choose the coefficient A1 such that f of 1 is 1, and therefore, we will obtain the Legendre polynomial So, if I choose the coefficient A1 such that it is 1, so therefore, P5 by of x becomes 5x cubed minus 3x divided by 2. So, I should choose A1 is equal to minus a half. Then you can see that P5 of 1 is 1. So, therefore, to summarize, we have found that the Legendre's equation 1 minus x square d2f by dx square minus 2x df by dx plus lambda f of x is equal to 0. It always has two solutions, but in general both solutions diverge at x equal to plus minus 1. Only when lambda is equal to L into L plus 1, that is lambda is equal to 0, if it is 1 and 2, L is 2, then it is 6, L is 3, it is 12, L is 4, it is 20. Only when lambda takes these of these values, then one of the series becomes a polynomial, and the polynomial solution is known as the Legendre polynomials, and you have, when L is 0, you have P0 of x, which is 1, P1 of x, which is just x. We have determined P2 of x from first principles, and that is half 3x square minus 1, and P3 of x we have just now determined equal to half 5x cubed minus 3x. Similarly, we can calculate P4 of x, which will be an even series with highest power of x as x to the power of 4, and P5 of x, the highest power will be x to the power of 5, and so on. So, alternately we will have even series, even polynomial, and the odd polynomial. These are the polynomial solutions of the Legendre's equation. So, therefore, the Legendre's equation is, I write it down once again, 1 minus x square d2f by dx square minus 2x df by dx plus L into, I write this down directly, L into L plus 1 f of x. These are the eigenvalues. So, L takes 0, 1, 2, etc. And I leave it as an exercise for you to find out when L is 0, then this term is 0 and the determination of the solution is extremely simple. I would like all of you to find out the two independent solution of this particular equation. So, one of the independent solutions will diverge and the other solution is the Legendre polynomials PL of x, which are alternately involve odd powers of x and even powers of x. These Legendre polynomials in the domain plus and minus 1, they satisfy the following normality orthogonality condition, that is minus 1 to plus 1 PL of x and multiplied by PL prime of x dx is equal to 0 if L is not equal to L prime, and if L is equal to L prime, then this becomes 2 by 2 L plus 1. So, I can write this down as delta LL prime, where delta LL prime is the Kronecker delta symbol, which is equal to 1 if L is equal to L prime, is 0 if L is not equal to L prime. And so, therefore, we can define the normalized wave function psi L of x as under root of 2 L plus 1 by 2 PL of x. They form a complete set of orthonormal functions in the domain x lying between plus 1 and minus 1. The orthonormality condition is minus 1 to plus 1 psi L prime of x. Actually, if I take the complex conjugate, it is the same function. So, psi L of x dx is equal to delta L L prime. And any arbitrary well behaved function, say f of x, can be expanded in the domain minus 1 x like as a in the domain C n psi L of x. This is something like a Fourier series where L goes from 0, 1, 2, 3 to infinity. Any well behaved function can be expanded and the coefficient C's of n can be determined by using the orthonormality condition of the Legendre polynomials. So, therefore, we had solved the problem. We started out by trying to find out the eigenvalues and eigenfunctions of L square. We said that first we said that we wrote down this is equal to lambda h cross square y theta phi. We first showed that to summarize y theta phi, the phi dependence, the theta dependence if I write as f of theta, then the phi dependence will be phi of phi, and phi of phi is the normalized function was 1 over root 2 pi e to the power of I m phi, m equal to 0 plus minus 1 plus minus 2. Then we considered the m equal to 0 case and we converted this equation into the Legendre equation, and we found that for m equal to 0, lambda was equal to L into L plus 1. Actually, if one solves this equation directly, and we will do that slightly later after about 10 lectures, we will do that the eigenvalues of L square is always L into L plus 1. So, the eigenfunctions are denoted by y L m theta phi. These are known as the spherical harmonics, the expressions for which we will derive little later, L into L plus 1 h cross square y L m theta phi. You must remember these formulae, and Y L M are such that the phi dependence is of this form, and therefore, these are also eigenfunctions of the operator L z, as we had discussed earlier. Y L M theta phi is equal to m h cross Y L M theta phi. You may recall that the operator representation of L z was equal to minus h cross delta by delta phi. We had derived this, and since the phi dependence is of this form, so therefore, L z operating on Y L M theta phi is equal to m h cross. Further, we will also show that for a given value of L, m lies between minus L to plus L. So, when L is 2, so when L is 2, m will be minus 2, minus 1, 0, plus 1, plus 2, and we will discuss this in greater detail after about 4-5 lectures. So, these are known as spherical harmonics. These are known as spherical harmonics, and they are simultaneous eigenfunctions of the operator L square and L z. The eigenvalues of L square is L into L plus 1 h cross square, where L takes the values 0, 1, 2, 3, etc., and the eigenvalues of L z are m h cross. So, what we have already determined is for m equal to 0, for that Y L comma 0, when m is 0, then we have shown that these are the Legendre polynomials. So, we have the normalized Legendre polynomials are 2 L plus 1 by 2 P L of x. Remember that x here is not the x y z coordinates, but it is x is equal to cos theta. In fact, I think it is better to write mu is equal to cos theta, so that not to confuse within the x coordinate. So, Y L 0 we will write as 2 L plus 1 by 2 P L of cos theta, that is mu, multiplied by the, when m is 0, then the phi part is just 2 pi, then the phi part is just 2 pi. So, this will become, this is the spherical harmonic 2L plus 1 by 4 pi P L of cos theta. So, there are two formulae that we have found out. One, that L at m equal to 0, Y L 0 are spherical. This we have derived from first principles. L is 0, 1, 2, 3, etc. L is equal to 0, 1, 2, 3, etc. We have also shown that Y L m is equal to f x f of theta or mu multiplied by 1 over root 2 pi e to the power of I m phi. And these are simultaneous eigenfunctions of L square operator and L z. So, that completes the angular momentum problem. We will, once we introduce the Bryant-Cat algebra, we will find out the complete solution to the problem, and we will give you a recipe for calculating almost any spherical harmonic. But at the moment, we have just solved for the m equal to 0 case, but we will do the general case little later, maybe about 5-7 lectures later. So, with this understanding of the angular momentum problem, we now go ahead to solve the hydrogen atom problem. So, we will solve the hydrogen atom problem, the simplest atomic problem, and also we will solve the deuteron problem, which consists of a neutron and a proton. As we all know that the hydrogen atom actually consists of two particles. One is the negatively charged particle and the other is, this is the electron and this is the proton. But the force between the potential energy between these two depends only on the magnitude of the distance between the two. In this case, if you use the CGS system of units, so then this is ZE square by R. If you are using MK system of units, then this is ZE is the charge of the proton, charge of the nucleus. So, in the case of hydrogen atom, Z is 1. So, you have Z q square by 4 pi epsilon naught R. So, this is in the MKS units, this is in the CGS units, where we are considering the hydrogen like atom problem. So, we have either one proton and one electron, or we can have Z protons and only one electron. So, something like helium ionized, helium ion. So, we have a nucleus which consists of 2 protons and 2 neutrons and only 1 electron. So, we are actually considering a 1 electron problem, 1 electron atom. So, that is the hydrogen atom or the singly ionized helium atom or doubly ionized lithium atom or something, whichever has 1 electron circulating it. Now, since we have 2 particles, it is really a 2 body problem. It is a 2 body problem. So, we write down the Hamiltonian, the total energy is P1 square by 2 m. This is the kinetic energy of the electron, this is the kinetic energy of the proton or of the nucleus, plus the potential energy. Now, we assume, which is true in the case of the hydrogen atom, that the potential energy depends only on the magnitude of the distance between the 2 particles. This is known as a central force model. That is, here is the proton and here is the electron. The potential energy depends only on the magnitude of the distance between these 2. So, if the proton, I write down the coordinates as x1, y1, z1, this is the r1 vector whose coordinates are x1, y1, z1, and the electron has the coordinates say r2 vector whose coordinates are x2, y2 and z2. Then the potential energy depends only on the magnitude of the distance between these 2, as it is indeed the case for the Coulomb potential. So, our objective, what is our objective? Objective is to solve the Schrodinger equation. Now, it is a function of 6 coordinates. So, I abbreviate this and write this as R1, R2. This is equal to E times psi of R1, R2, where R1 vector is an abbreviation for x1, y1, z1 and R2 vector is an abbreviation for x2, y2, z2. So, we are really considering 6 coordinates, 3 of the electron and 3 of the proton. How to solve this? So, we will have, so P1 square will be, let me write down h psi. So, this is minus h cross square by 2 m1 delta by delta x1 square plus delta 2 by delta x2 square, sorry y1, sorry I am sorry, let me rewrite this again. This is minus h cross square by 2 m1 delta 2 by delta x1 square plus delta 2 by delta y1 square plus delta 2 by delta z1 square psi plus P2 square by 2m2, that is plus, that is minus h cross square by 2m2. Again you will have delta 2 by delta x2 square plus delta 2 by delta y2 square plus delta 2 by delta z2 square psi, which is now a function of x1 y1 z1 x2 y2 z2 is equal to E psi. I'm sorry, plus V times psi. Now I leave you as an exercise for you to prove that if I try to separate the variables like this, psi of R1 and R2 like this, say psi 1 R1 and psi 2 R2. If I assume the separation of variables like this, and if I substitute it in this equation, because the potential energy function depends only on the magnitude of the distance, the variables will not separate out. The variables will not separate out, and so therefore the method of separation of variables will not work. The method of separation of variables will not work, and therefore in order to solve this equation, we have to introduce the relative coordinate. The relative coordinate is represented by r, which is r1 minus r2. This means that we introduce the relative coordinate x as x1 minus x2, y as y1 minus y2, and z as z1 minus z2, small z. These are known as the relative coordinates. And then we also introduce the center of mass coordinates. The center of mass coordinates, and this I write as r is equal to m1 r1 plus m2 r2 divided by m1 plus m2. So therefore the x coordinate of that, which I denote by capital X, that will be m1 x1 plus m2 x2 divided by m1 plus m2, and similarly y and similarly z. So instead of the coordinates x1 y1 z1 x2 y2 z2, these are 6 coordinates, we write down, we try to transform the equation in terms of these 6 coordinates: small x, small y, small z, and capital X, capital Y, capital Z. And please see, small x and capital X involve only x1 and x2, small y and capital Y only involve y1 and y2, and small z and capital Z only involve z1 and z2. So that makes life much simpler. And let me do a little bit of algebra. So we have to calculate something like delta 2 psi by delta x1 square. So first we must calculate what is delta psi by delta x1. So if I transform this, so I will get delta psi by delta x times delta x by delta x1 plus delta psi by delta capital X times delta capital X by delta x1. Now I need not consider delta psi by delta y, because delta y by delta x1 will be 0, because x and x depend only on x1 and x2. So what is delta x by delta x1? So that is 1. So we will have delta psi by delta x plus delta x by x1 is m1 divided by m1 plus m2 delta psi by delta x. Now, I want to obtain this. So, you have to differentiate this once again. So, let me do this carefully. So, we will have, let me do this carefully. So, delta 2 psi by delta x1 square will be, now if I differentiate this, so you will have delta by delta x times delta psi by delta x by delta x1, which was 1, plus delta by delta x of delta psi. You have to do it little patiently, multiplied by delta x, capital X by x1, and that we have just now found to be m1 by m1 plus m2 plus the second term. So, you will have m1 by m1 plus m2. First, I differentiate this term with respect to x. So, I get delta by delta x of delta psi by delta x times small delta of x divided by delta x1, this is 1, this is unity, plus delta by delta x 2 psi by delta x square, and then delta x by delta x1, that is m1 by m1 plus m2. It's little cumbersome, but very straightforward. So, you write this as this is equal to delta 2 psi by delta x square plus delta 2 psi by delta x times 2 m1 by this term, and this term will add up, m1 plus m2, and then this will be m1 by m1 plus m2 whole square. So, m1 by m1 plus m2 whole square delta 2 psi by delta capital X square. Now, as you had seen that I must multiply this by minus h cross square by 2 m1. So, if I multiply this by minus h cross square by 2 m1, so I will obtain minus h cross square by 2 m1 delta 2 psi. Oh, let me write down first this equation, that delta 2 psi by delta x2 square, if I right. So, we will obtain the same expression, excepting there will be a minus sign here. So, delta 2 psi by delta x square plus instead of plus sign here, we will have a minus sign. That is because delta x by delta x2 is minus 1. So, this equation tells us that delta x by delta x1 is 1, but delta x by delta x2 is minus 1. Because of that, you will have a minus sign here, delta 2 psi by delta x to m2 by m1 plus m2 plus m2 by m1 plus m2 whole square, and the same term delta 2 psi by delta capital X square. So, therefore, now I multiply the first equation by minus h cross square by 2 m1 and the second equation by minus h cross square by 2 m2. If I do that, you will get the following result. So, you will obtain minus h cross square by 2 m1 delta 2 psi by delta x1 square plus minus h cross square by 2 m2 delta 2 psi by delta x2 square. One has to be little careful. So, the first two terms add. So, you get minus h cross square by 2 1 over m1 plus 1 over m2. And you see, I divide by m1 here and I divide by m2 here, and this minus this will become 0. So, this term, the cross term will cancel out, and the second term will therefore be, if I divide by m1, so it will be minus m1, and from this it will be m2. So, m1 plus m2 divided by m1 plus m2 whole square delta 2 psi by delta x square, capital. Oh, I am sorry, this I forgot to write here, delta 2 psi by delta x square. So, if I add these two terms, then I will finally obtain this. The reduced mass of two particles is defined by 1 over mu is defined to be equal to 1 over m1 plus 1 over m2. So, therefore, this equation becomes minus h cross square by 2 mu delta 2 psi by delta x square, and this becomes minus, oh, I forgot to, so minus h cross square by 2 capital M delta 2 psi by delta x square. Similarly, for the y dependent term and the z dependent term, and therefore, we finally obtain. So, the second, so to this we must add delta 2 psi by delta y square, delta 2 psi by delta z square, and here we must add delta 2 psi by delta y square plus delta 2 psi by delta z square. So, therefore, the Schrodinger equation which was h psi is equal to E psi, and if you remember, this was minus h cross square by 2 m1 delta 2 by delta x1 square plus delta 2 by delta y1 square plus delta 2 by delta z1 square minus h cross square by 2 m2 delta 2 by delta x2 square plus delta 2 by delta y2 square plus delta 2 by delta z2 square plus v into psi is equal to E psi. Now, we had shown, we had just now calculated this, and we had found that these 6 terms become from here minus h cross square by 2 mu delta 2 by delta x square, this is the relative coordinate, delta 2 by delta y square plus delta 2 by delta z square psi minus h cross square by 2 m delta 2 by delta capital X square plus delta 2 by delta capital Y square plus delta 2 by capital Z square psi plus V psi is equal to E psi. Now, this V depends only on R. And what is r? X square plus y square plus z square under the root. It does not depend on capital X, capital Y, capital Z. So, now we assume that the psi is a function of small r vector and capital R vector. And if we now use the method of separation of variables, if we now use the method of separation of variables and assume that psi of r comma r is equal to psi of r and say phi of r capital, and if I substitute it here, because the potential energy function now depends only on small r, the variables will separate out, and that is a major simplification of the problem. For any two body problem in which the potential energy function depends only on the distance between the two particles, can always be reduced to this. And as we will show just now, one will describe, one of the equations will describe the uniform translational motion of the atom as a whole like a free particle, and the second term will describe the internal energies of the hydrogen atom. Now, this will be true even for the neutron proton problem, which is the simplest problem in nuclear physics. If we assume that the potential energy between the neutron and proton depends only on the distance between the two particles, then that particular problem, which involves the Schrodinger equation, involves 6 coordinates, can be transformed to 2 equations, one describing the internal motion of the deuteron, and the second is the uniform translational motion of this, of the nucleus as a whole. So, in the hydrogen atom problem, we transformed this to 2 coordinates. One was the relative coordinate and the other was the center of mass coordinates. So, the hydrogen atom as a whole, as a free particle, moved, as I will show in a minute, moves as a whole, and then there are internal motions between the electron and the internal motions of the atom, which will lead to the discrete states. But that there the mass has to be replaced by the reduced mass. In the case of the hydrogen atom problem, since the proton is very much heavier than the electron, the reduced mass is almost the mass of the electron. But in the neutron proton problem, where the mass of the neutron is almost equal to the mass of that proton, the reduced mass is about half of the neutron mass or half of the proton mass. So, there it makes a tremendous amount of difference. So, you see, now we will substitute this here, and if this will require a little algebra, which I would request all of you to do. If I substitute it here and divide by psi times phi, then we will obtain the following equation: minus h cross square by 2 mu 1 upon psi delta 2 by delta x square plus delta 2 by delta y square plus delta 2 by delta z square. This from now on we will represent by del square psi. So, this will be one term plus, since we have divided by psi and phi, so this will be just v, which depends on r coordinate, and then there is the second term minus h cross square by 2 m 1 upon capital phi, and so delta 2 by delta capital X square plus delta 2 by delta y square plus delta 2 by delta z square, capital phi. This we will have equal to E, because we have divided by psi. We had written psi is equal to small psi, which depends only on the r vector, multiplied by capital phi, which depends only on the r vector, and we have divided the whole equation by psi times phi. So, we now set this is equal to the E, the center of mass. So, we write this as so this is the energy corresponding to the center of mass. So, we write this as E c, and this total thing we write it as the relative energy. So, E r plus E c is equal to the total energy of the system. So, let me write down the E r portion. So, minus h cross square by 2 mu 1 over psi del square psi plus V is equal to E of r. So, we will obtain del square psi plus 2 mu by h cross square E r minus V of r psi is equal to 0. Please see, there is a difference. This is r vector and this is just r. This is the modulus of the r vector. So, this describes the internal motion of the hydrogen atom, and we will solve this. And the second one will be minus h cross square. Let me write it down on a separate page. So, this equation will be minus h cross square by 2 capital M 1 over phi delta 2 by delta x square capital plus delta 2 by delta y square plus delta 2 by delta z square is equal to the center of mass energy multiplied by phi. So, we can write this as delta 2 by delta x square plus delta 2 by delta y square plus delta 2 by delta z square phi plus 2 m E c by h cross square. So, p square by h cross square phi is equal to 0. So, this is the Schrodinger equation for a free particle. So, I can write this down as phi of r will be equal to some constant e to the power of I p dot r by h cross. All values of p square will be allowed, and so it will, this is the center of mass moves as a free particle. The center of mass moves as the whole hydrogen atom is moving as a whole, and all values of the energy are allowed. So, therefore, the center of mass moves as a free particle with energy p square by 2 m. M is the total mass, that is m1 plus m2, where m is the m1 plus m2. So, we have this part, and then the second part will be this particular equation. We will, and the total energy of the atom will be equal to the relative energy, which we will find to be discrete, plus the center of mass energy. And the center of mass itself behaves like a free particle, and what in our next lectures we will try to solve this particular equation for the hydrogen atom problem. So, let me write down what will be the starting point of the next lecture, that del square psi of r, this is the relative coordinate, plus 2 mu by h cross square. I will remove this subscript r, minus v of r psi of r is equal to 0. This will the solution of this equation will determine the energy states of the hydrogen atom. Once again, r vector is the relative coordinate and small r is the magnitude of the relative coordinate, because the potential energy function depends only on the distance. And as I had mentioned, this analysis that we have presented is valid for any spherically symmetric potential. Any potential energy function for which the potential energy function depends only on the distance, it need not be just Coulomb, only on the distance will be described by the analysis that we have presented today. Thank you.